Hi, it's Mike VI3MW, and we're here at the QSO Today Expo. We're recording this a couple of weeks before the actual Expo, and I'm fortunate enough to have Steve Hicks, N5AC from FlexRadio, our Chief Technical Officer. Steve, thanks for taking time to join us.
Hey, thanks, Mike. It's good seeing you.
Yeah, I know it's been a crazy 18 months, and we wish we could share more with you on that, but you'll have to trust us on that one. So we're going to go through a bunch of Steve's history of Flex Radio and talk about a few things about the technology, and hopefully you'll find some cool, interesting stuff that Steve can share with us. Now, Steve, you've been a ham for quite a while, right? And you really love the microwave part of the hobby.
Yeah, I got licensed when I was 12, and my dad's a ham. I got licensed when I was 12, and then went off to college, not right then, but a little later, and got my extra when I was in college. And I don't know, later kind of got interested in microwave roving and that sort of thing. That's kind of the aspect of hobby that I really like.
You know, we can see that on all our radios because is that why there's sequencers and multiple push-to-talk outputs?
That's right. In fact, I was recently asked by a government group that we were working with. They wanted to know how high in frequency our radios would go, and I said, well, we programmed them to go up to 999 gigahertz, but we've only tested them up to 78. So they were surprised to hear that.
I guess your kids didn't like you drive them to school with that?
No, my kids, I'm trying to think what age they were when I had the Rover all set up and decked out, but I want to say they were in middle school and early high school, and well, they actually didn't mind the Rover that much. They were young enough, I think, maybe middle school, that when I would pick them up, their friends would say, "Hey, what is that? You know, is your dad a storm chaser?" Which I also happened to do, but none of the equipment on there was, for storm chasing. But I don't know. When they got in high school, it got less cool.
Drop me off a block away.
It's like, what is your dad doing?
You ended up at Flex Radio. I think Gerald reached out to you. Somehow you guys met, right? And then he was working on a project. You had the expertise.
Yeah. So I had come down. I come down to Austin Summerfest, which is a ham fest we have in Austin, and I come down about every year. I was living in Dallas at the time, and had taken some time off. I worked for a couple of companies that had gone public. And I had started doing a lot of roving work, and I found that I was using a crystal oscillator for all of my transverters in my truck. And like when I would rove in the January contest, I'd keep it, 70 degrees inside the truck, and the transverters would all be warm and right on frequency. And I'd open the doors, and the cool air would rush in, and they would drift off frequency, and I'd have to call and tune around and find people and all that. So I created a GPS locked oscillator. Just kind of a, necessity is the mother of invention sort of thing, and put that on my transverters. And I happened to be talking about it at the Central States VHF conference, and Gerald was in the audience and came up to me afterwards. But I had met him briefly before, like I said, at Austin Summerfest, and had seen what he had done moving from the little 3-board SDR 1000 stack to the Flex 5000. I was real impressed with what he had done. So he came up to me after this Central States deal and said he had bid on a government contract to build a multi-channel receiver, and wanted to know if I'd be willing to help him. And at the time, my career was all based on software. That's what I'd done my entire career. I'd worked for Digital Equipment and a number of other software companies. And I told him, no, you want a hardware engineer. And so I gave him a few names, and he talked to a few of those. And I don't know, the more I thought about it, I got more interested, and he wasn't really that interested in the folks I'd given him names of. So I came down and talked to him, and we talked through it. And what he really needed was somebody that could do digital electronics and software. And I have a double E and done a lot of digital electronics in college and really liked that sort of stuff. So I agreed to do it. And we built a 32 channel narrowband receiver. When I say narrowband, I mean a couple hundred kilohertz instead of, megahertz. And it's a HF receiver, and one of the key things about it is that it's coherent. So you can take all 32 channels and tune them together. And so this product ended up getting used for direction finding and that sort of thing in the government. And so that kind of started my career off here at Flex Radio.
And I guess shortly after that would have led you into internally we call it Deep Eddy, but the 6000 design?
Well, so the 6000 design, one of the things we did with that particular product that I had been brought on board to build with Gerald was we also built a wideband sampling receiver also along with that product. And it was a PCIe card that plugs into a PC, and it has 16 receivers on it. And you can talk to those receivers from inside the PC and tune them wherever you want. It had an antenna spigot that goes on the back of the PC. That was a pretty neat product. That product's called SCRX, and we made that available. And the neat thing about it was we had never done wideband sampling before, and it was fairly new in the industry. I mean, people were doing it, but it wasn't being done a lot. And the general consensus in the community was that it was not as good as narrowband receivers. And so Gerald had done a lot of research on what was possible and how to make it the best receiver we could. And as part of that, we were given access early. We talked to a number of vendors about what we were trying to do. And one of the vendors, Analog Devices, gave us early access to an analog to digital converter that was brand new on the market, hadn't been announced. And I think we got it a year or two before it was available commercially. And when we built that SCRX receiver around it, we found that it was actually a better receiver than the narrowband receivers we had built, to our surprise and to the government's surprise. So that was a really neat deal. And we looked at that and said, gosh, we could go make an amateur product out of that. So we started dreaming about, what that product would look like and what it could do. And, like we had 16 receivers in that SCRX product. And we said, well, an amateur product, I can't imagine anybody using more than 8 right off the bat. So we went and put 8 receivers in that, and that became the 6700. But at the time, the code name for those products internally that we use, we always give products code names so we can talk about them without people, if we talk about them at lunch, people don't know what we're talking about. But the whole series of radios that was designed around was called the Storm series. And that first radio, the 6700, is called Microburst. And then we had other radios that came after that, Tsunami and I don't know, other kind. I forget what we named them all. But yeah, the Deep Eddy was a follow-on to that, which is the 64 and 6600. And we moved away from the 6700, which was more of a monolithic design where we had one board that had all the receivers and all the front end of the radio and the microprocessor and all that on one board. And there's a number of reasons we did that. One of them was that the tolerances for example, that there's a microprocessor on that board that has a DSP and an ARM in it, and it has DDR3 memory on it. And the line widths of wires on the circuit board going to the memory are 4 mils. That's 4/1000ths of an inch wide, and the spacing between them is also 4 mils. So it's what we call 4 mil space trace in the industry. And the boards like that are not terribly difficult to make, but they're more difficult than other things. And you typically want to minimize the size that you do that. And the 6700's, main board was like a foot by a foot kind of thing. So it was very big, and it made that board a little bit more expensive and difficult to build. Plus, we couldn't swap out new technologies as easily. We'd have to go redesign that board. So as a result, what we decided to do was to modularize that, and that is what Deep Eddy's all about, which is a separatable FPGA and processor and all that kind of stuff, so we can mix and match those as time goes on.
Yeah, that really does make
question.
No, that's great, and that makes it scale for the future too, in theory, right? So,
right, that's exactly what it's about. Yeah.
In part of the design that you've learned when we moved into the 6000 series, we use a different method and technology for ensuring or limiting, I guess is the word, front-end overload, because there's a lot of stuff all over the internet about software-defined radios, or direct sampling to be more correct, because I call SDR a technology more than a build technology, because that's what it is. We've gotten away from coils and noisy mixers and stuff into direct sampling. In the direct sampling world, do we experience sort of front-end overload or SDR overload that others have talked about?
Yeah, so overload is kind of a complicated topic, and let me see if I can break it down. There's a number of different things that happen here. If you look at a direct sampling receiver, there is an analog portion of that front end. So any A to D converter, which you ultimately use in the radio, has a noise figure on the front of it that's somewhere in the let's say 25 dB-ish range. It could be more or less than that, just depending on what converter you have and all that sort of thing. Well, for 6 meters, for example, you need a noise figure that's in the 6 dB, 6 to 10 dB kind of range. in order to operate. And it gets, you can have a worse and worse noise figure as you go down. At 10 meters, I don't know, 10 dB is probably fine. At 20 meters, it might be, I don't know, 14 dB or somewhere in there. So you have to put some sort of front end on that analog to digital converter that has gain. And so what everyone tends to do is put a low noise amplifier on the front of it that has a good noise figure and enough gain to overcome the noise figure of the analog to digital converter. This isn't a bad thing. It's just the way things are designed, and it's, it's very, very normal. But what happens is that the amplifier that you put in front of the analog to digital converter has a maximum amount of input that it can take before it goes into compression. And this is the same kind of compression that we talk about with power amplifiers and all that. If you put too much signal in it, it will begin to compress. And what you want with an amplifier is it to evenly multiply your signal. So if you put, plus 0 dBm in and it's a 10 dB gain amplifier, you want plus 10 out. You put plus 10 in, you want plus 20 out. But you get to some point where let's say you put plus 30 in, you only get plus 34 out. It won't do the 10 dB gain because it's in compression. And so that compression is what we would call analog overload. And in the analog world, there's usually there's a soft element to that. It's kind of like, if you listen to guys talk about old tube amplifiers and they drive them into compression, the tube amplifiers are soft. And people that are tube amplifier aficionados will say they sound better in an audio amplifier because of that. It's the same kind of thing. So there's this analog input overload thing that can happen. And then once you take, let's say you're not an overload there, that you've got a signal that's low enough, an S9 signal or something going in, it makes it through the amplifier, gets into the analog digital converter. Now you've converted that signal into a numerical analytic signal that's a bunch of numbers in a microprocessor. Well, those numbers you're fitting into a number space. So let's say that you're using 16-bit I and 16-bit Q, which are in phase and quadrature, to represent that analytic signal. If you do anything to increase the size of those numbers where it goes beyond 16 bits, and 16 bits would be, the number would be 65,535. So if the number gets larger than that, you have to do something to solve that problem. And the most common thing to do is to truncate the number, and that's called digital overload. And so each of those has artifacts that appear in the radio if you go into either one of them. So when you go into digital overload, you take a signal which might look like a sine wave gradually, having a peak, and it's going to go up, and then it's going to hit that maximum number and go straight across and then go down, that sine wave would. And what that'll do is create lots and lots of harmonics. And so in the SDR world, a digital overload causes a very gruff and nasty overload. You see lots of spurs show up from all those harmonics and stuff. And it's very visible in the noise floor, especially if you have a pan adapter or waterfall, what's going on. So that's digital overload. In the analog world, it's not as bad. You get analog artifacts like distortion, those kind of things, but they're not as bad as you would see in the digital world. So one of the things we did in the radio, understanding all that, is we made sure that even as you enter analog overload, on the digital side, we don't allow you to enter overload. And so we have enough bits in our back-end digital processing so that the radio can enter analog overload without entering digital overload. And the result of that is that when you overload the front end of one of our radios, they look a lot cleaner because we don't allow them to go into digital overload. So that's something that we do different. It costs a little more because you have to put more bits in the back-end processing, and you have to do more multiplies and all kinds of other stuff in the FPGA. But it makes the receiver operate much better when it gets into an edge condition like that, where you've got more power coming in the front end than you'd like. Does that help you?
Yeah, yeah, it did actually. And for some of the basics here, I'm fortunate to have a bit of education, but when you have sine waves and then if you have a square wave, it actually produces a ton of harmonics, which is what you don't want, because a square wave is a collection of harmonic frequencies, correct? Is that the simple? If I remember my college education in that world, but
your Taylor
cool.
series.
We have a cool feature in our Flex 6000 series radios called controlled envelope single sideband. And it's our AGCT, it's probably one of the least known cool features we have, and we should probably tell more people about it.
Yeah. So the kind of story about how we ended up with this technology is I was at Dayton one year, and Gerald and I are always both interested in helping people create new technology and getting new technology to the public and all that. That's kind of our bread and butter. And so this guy came up to us, David Hirschberger at Dayton, and said, "Hey, I got this idea." And he kind of walked through the idea, and he said, I'm really sure this will work, and here's some of the benefits of it and all that sort of stuff. And I listened to it. It sounded really cool. So I wrote his name down. I said, yeah, let me give you a call after the show and let's talk about it some. And then probably 5 minutes after, he stopped by, a friend of his stopped by that I happen to know fairly well that used to work at the same company he used to work at. And he says, hey, if Dave says this is going to work, it's really going to work, and you should listen to Dave. I said, yeah, good deal. I'll give him a call. So I called Dave, and he walked through the idea, and really great idea about how to do what essentially amounts to compression or speech processing with very low or no distortion. And so if you've been a ham a long time, I know you've probably encountered speech processors. One of the first ones I used was on a Yaesu, I think it was a 757 GX or something like that. And if you turn the processor on and turned it up, you kind of sounded like a robot. And I'm not trying to give Yaesu a hard time. For the time frame, that's what the technology was like. And so I talked to Dave, and Dave said he'd like to develop this technology. And I said, well, we'll send you a radio, and we'll work with you to develop it and make it work on our radio right out of the chute. So we did that and worked with Dave real closely. And he ultimately published an article in QEX. You can go find this article there on how the technology works. It goes into great detail about it. But the net for us is that when you turn on our speech processor, it does use this as the underlying technology. We made a few tweaks at it at FlexRadio to get some more benefit out of it. But the net is you can get up to 2.5 dB out of a sideband signal more power than you would normally. And it's very, very minimal distortion. And it really sounds great and gets you more power. So it's like instead of having a 100-watt radio, you have a 200-watt radio, or instead of having 1,500 watts, you got 3,000 watts. So it's a really neat technology.
Yeah, and especially on the low bands, like 160, 80, for some people even 40, getting that sort of gain is a huge, huge number. And Dave actually is speaking at the QSO Today Expo. We reached out to him, and he was he thought it was great. And what a nice guy too, because I sort of got to meet him and talk to him. And so that you can find that in the list of presenters as well if you want to learn more about controlled envelope single sideband. And I have to give FlexRadio credit, because between you and Gerald and everybody else, the door has always been open for developers to take the platform and try something new and unique. And you guys have always been very supportive, and which of course is going to lead us a bit more into the API and maybe waveforms. But in case you're not aware, we have an API, and if you want to write your own whatever, you can talk right to the radio. Use the same code we use, correct? Or the same interface we use.
Yeah, when I was, I'd gotten licensed at 12, as I mentioned before, and I got my extra when I was at college at Texas A&M. And one of the first radios I bought with my own money was a Kenwood TM721, which is a dual band VHF, UHF radio. And I did a lot of stuff with, both FM, but also packet radio. I ran a packet bulletin board out of my apartment in college and did some things like that. And one of the things that was kind of on my mind at the time was I wanted to be able to write software inside the radio and make the radio do what I wanted it to do. And I was disappointed that in the ham radio world, when you buy commercial equipment, you can't do any of those things. And so when I just through a fortuitous event ended up at FlexRadio, I kind of felt like, who was I not to be the guy that, added those capabilities. So, we talked it over and decided to make our API open. And not only that, but we eat our own, I say we eat our own dog food, because if you run Smart SDR, it actually uses our API to talk to the radio. So literally anything you see us do in Smart SDR, you can do with anything that you design external to the radio. And then, as you mentioned, we went ahead and added a waveform API a few years after that. And the waveform API allows you to create your own mode in the radio. So if you don't like sideband and FM, you want to create your own mode, you can do that. It can run either external to the radio or internal to the radio. You can create that mode and run the application, and it can actually, through an API call, cause Smart SDR to show your mode in the client interface, Smart SDR that runs on a PC. You can select it and then use your mode. So it's really powerful.
Wow, I could see that, from an amateur world, certainly commercial world too, where you have different licensing flexibility, I guess. We obviously have to be non-encrypted and everything, but that's great. And I think I jokingly said earlier to someone, I guess we could, in theory, write a DMR API if you really thought it was going to be useful or, more efficient. But I guess ideally in the HF world, we'd want to sound like FM and take up a kilohertz of bandwidth would be a better use of an API type of thing.
You can do anything in the API, most anything. Some of the modes that are TDMA, which stands for time division multiple access, the ones where you have to transmit in a certain slot or listen to a certain slot, we've only recently added timing information to the waveform API. So those were not possible before, but they are, or we haven't released all that code yet. That's one of the things we've been working on lately, but that will allow some of those kind of things to be done as well.
Wow, you really could sound like FM on HF then, if you wanted to. And is essentially US, like upper sideband and lower sideband, are they essentially a waveform API under the covers?
They operate very similarly. What we have under the covers is there's what we call a signal chain, and the way it works is let's say on the receive side, the analog digital converter hands samples for that particular receiver to a block of software, and that block will go do whatever it's supposed to do. So in the upper sideband signal chain, if you want, there's the demodulation portion, but we also have noise blanker, noise reduction, all the other things that happen to that signal as you process it. And then ultimately on the receiver side, it outputs that, and it goes to the essentially to the codec, which provides output on the speaker. And the opposite happens on the transmit side, where we take in audio from the microphone, we modulate it, do anything else, filter it, and then put it out through the transmitter. So any of those blocks that we have in there for those modes, you could go write your own block like that and put it in the waveform API, and instead of doing sideband, you could do whatever else. This is how we added codec 2 and D-Star to the radio using this API.
One other thing that we've done differently with this radio than we learned from Power SDR is we do all the heavy lifting in the radio. All the big math is done correct in the radio, and we did this for a very specific reason.
Yeah,
and
so
that is
when Power SDR was, it's what we used on the SDR 1000, the 5000, the Flex 3000, some of those early models in 1500. The radio was more of a kind of a dumb box. It would take the signal off the air, bring it down to baseband, and then hand the IQ signal as digital data to the radio over a communications interface, which was in the early days, it was it was a sound card interface real early, but then it became FireWire and eventually USB with the Flex 1500. And then at that point, all of the things I just talked about in the signal chain, the processing of that signal would occur inside the PC. Because the PC has lots of power and you've already got the PC on your desktop and that sort of thing. So it made it very easy. But one of the things we learned out of that is that that makes the PC and the radio become this system together where you couldn't cause any interruption in anything that happened there without negative consequences. So we would have people that had virus scanners, which would kick off while they're transmitting, and it would insert, short blips of no audio or whatever in their transmit. And we had to work around all those things in that world. So that was one of the key reasons we shifted to the architecture that we did, which is more of a client-server architecture from an IT perspective. The other reason is that in order to process larger and larger bandwidths to see more and more of the spectrum, you had to send more and more IQ data directly to the PC to be processed. So if you say, gosh, I want to look at the entire 10-meter band, you had to send multiple megahertz of data, megahertz times the number of bits to the PC, and it required this big fat pipe going from the radio to the PC. So it made remote operation practically impossible because you couldn't send all that data over the internet. So by placing all the compute power inside the radio and doing that processing inside the radio, now all we have to send to the client interface, which might be local or might be remote, is a very small amount of data. It's just enough like for a phone call for audio, plus the data to control and display the spectrum. And we also give the user in Smart SDR a lot of control over that so he can control his bandwidth. So if you're on a very narrow pipe, let's say you're somewhere that only has ISDN level throughput, you can go take your pan adapter and a waterfall and turn the speed of those down and use less than 200K of kilobits per second worth of bandwidth on your connection. So that's kind of what all that was about. And we achieved, all the goals we set out to by changing the way that technology worked.
Yeah, amazing stuff. And this is why today you can pull out an iPhone or an iPad or a Windows tablet and be on the air. It's just all, as you say, the client just needs to be a thin client or a light client. And who knows what the future will bring or what somebody else will develop for other platforms from Android, Chromebook, Linux. I mean, these are all doable, and the it's open, right? Feel free to muck around. We've already started to see some guys playing in the Raspberry Pi world. I've actually done headless, WSJT on a Raspberry Pi 4. And as I was telling Steve earlier, somebody else did the work. I was just following the cookbook on the community and went, holy crap, it was just like one command to get the audio, DAX 1 through, and it's working. It's like one of those aha moments. That brings us into remote. And as I've probably said way too many times, but back in about 2012 or 13, when this early 6000 series came out, and I was not with FlexRadio, but I think I'd made enough noise at FlexRadio that the likes of Steve and Gerald and Eric, Ed, and Abed all knew my name, which is, I don't know, a good thing at the time, but we all saw the vision. And yeah, it was all okay. You still talked to me at Dayton, so that was okay. We didn't know scatter. I thought that was a good sign. And I could be a pain in the ass. I remember asking Steve clearly, I see there's a LAN connector. I had the brochure in my hand on the back of the 5300. And I said, what can I do through that? And you literally said everything. And I went, I saw the light. I just saw the light. And then that brought us into remote. So because we have remote literally built in, if you can move a TCP packet on a LAN or a WAN, you can do it with the radio. It's really just the way it's designed as well. And SmartLink makes that incredibly easy so that you don't have to be a VPN expert, network expert, or VPN person. We've designed it to make it's a bit of an advertising here, to make it about as plug and play as you can make it. And I admit it's pretty rock solid. We've had a few hiccups, but I'm pretty impressed with the way you thought it through, and really kiss simple when you think of it. So
yeah.
So.
When we had the FireWire and USB interfaces on the earlier models, each of those had their own problems, primarily because of drivers and interoperability and the cards that required to support them and all that. And USB is more universal than FireWire was. With FireWire, it very much depended on what platform you were on and what operating system and card and all the other kind of stuff you had, how well it was going to work and what the issues might be. But we had issues also with USB. But the real thing that drew us to Ethernet, two things. One was it was clear that it was becoming ubiquitous and that Ethernet was going to be on any device, and it had to work. You could not go to the store and buy a PC that said, we didn't include Ethernet and we don't think it's important, and so we didn't put it on this platform. Or if you were a manufacturer and you designed a PC and Ethernet kind of sort of worked but didn't quite work, you wouldn't be able to sell those PCs. People would try them and complain about them, and you wouldn't be able to sell them. Manufacturers, distributors would return them and all that kind of stuff. So the really neat thing about Ethernet is that it's ubiquitous and it works everywhere. That plus it also scales. So the early Ethernets were 10 megabit, and then they got 100, then a gig, and then 10 gig and 40 gig. And so it across the protocol level, which is, as you mentioned, TCP/IP or UDP/IP, all of that stuff from our software perspective is identical, regardless of what the underlying speed or physical layer is in the Ethernet. So today we might be running on wire-based 100 megabit Ethernet, and tomorrow it's gigabit Ethernet or fiber with 10 gigabit Ethernet or whatever else. So it's very nice from a software perspective to be able to write software and have it work across all that stuff. So we leveraged Ethernet very heavily.
Yeah, and it works really well, and you don't need gigabit in your house to take advantage of. We're actually pretty light communicator on your network. So, and I'm glad you brought that up because I'm doing a talk for the QSO Today Expo, a bit of a shameless plug, but I called it, I think, the death of the RS-232 port or cable or communications because it's half century old technology. And by the way, somebody sent me their debugging card. He worked for AT&T out of his wallet, right? All the levels, all 25 pins and what they all did. So I included that. But as you're going forward and if you're building your shack, consider external devices that are LAN-based from your rotor controller to your antenna switches and stuff, and you won't go wrong in the long term. Really makes a great foundation.
Very true.
Very true. Pause for a second. Remote. We've seen, I'm going to talk about remote a bit more. One of the side effects of COVID, where we all shut down in March of 2019, was we saw a huge spike in remote operations, not only with people using their, the radio was in a different part of the house or a different building or 100 miles away or, 1,600 kilometers, but they were sharing their radios a lot. They had friends that were sick or shut-ins or in apartment buildings, and remote really became a great idea and easy to implement, as I said. But with that, we also came up with MultiFlex. And I'm sure there's more things we could probably do with MultiFlex because it should scale. And if you're not aware of MultiFlex, Steve, tell us about the idea for MultiFlex and maybe a fairy tale of what we might have even thought about tomorrow. And I'm not going to hold them to anything because we've come off a long grind in another contract. And we talked about this before, and we're not even sure where we're going next, where it's written down and here's the plan, just other than a lot of great ideas. So go ahead.
Yeah, so we imagined that we would do remote from the day we came out with the Flex 6000 when we put the Ethernet connector on the back and developed a client server kind of approach to how the radio is controlled, where you have a control surface, which for us is Smart SDR that you see on Windows or iPhone or whatever else. You would be able to control the radio with that, and then the server portion that does all the work is actually inside the radio. So we envisioned that from the start as being something that would be very good for remote. And with SmartLink, we added that capability so you can use your radio remotely. We do have a server that runs in the cloud, and the purpose of the server is to connect. It's like a broker that connects your local device, which might be an iPhone or PC or whatever, to your radio, which might be somewhere else in the country or in the world. It connects those two together. And once they're connected, then you can talk directly. So you don't actually go through our server once you've done that. And so that was really neat. We spent a bunch of time working on that and getting it up where everybody could use it. And it's very widely used capability of our radios, and it's regarded as the best remote solution in the industry. And then we looked at that and we thought some about people that don't have the opportunity to have a radio or station in front of them. And is there a way to let those people get Elmers and use the radio remotely when somebody else isn't using it, or even when they are using it? So since we have multiple receivers in the radio, we thought, hey, why don't we go enable it so somebody else can log into your radio even while you're using it and put a receiver on and operate that radio. So let's say you got a buddy that's a shortwave listener or somebody that wants to become a ham and listen and try and understand what that's about or any of those kind of things. MultiFlex allows the person to go log into your radio remotely while you're using it or while you're not, and use it at the same time. So that's kind of what it's about. And there's a lot of different uses for it. One of them is you could actually run two guys in a contest sitting next to each other using MultiFlex on the radio, because some of the contests you can have two operators but only one transmitter on at the same time. So this allows you to do that using a single radio, which is a really neat capability. But it also allows things like, if you want to let your grandkids log into your radio and try out listening to ham frequencies or shortwave listening, you can do that, or let a buddy use your radio or whatever.
Yeah, very good. And I'll answer the question. I know some of you were thinking, there's not enough security there. Is there, can I control the power of the bands, the SWL mode? And believe me, these are ideas we're very well aware of. And to be, because it's just exploded from where we've gotten. We have a lot of clubs running remotes, and they've asked for that sort of protection and login stuff. So we're well aware of that as coming up. And N1MM has a new feature, and I'm trying to remember it correctly. It's sort of a distributed keyboard. So the idea is two guys could sit down in a CW contest and use a single headphone splitter, and one guy could start typing in the call sign, the other guy would see it in his log entry window. Well, in the Flex world, it gets even better, because he could also be on a different frequency, yet still seeing the different or the same, and helping him out, and even more so in a mentoring role for a CW contest if you're that type of operator, or even sideband. All cool features. So we're seeing more and more in this distributed information sharing world, and my hat's off to the guys at N1MM for their vision too. They just keep moving stuff forward, and we integrate really well.
Yeah,
with N1M.
Yeah, you mentioned land enabled applications and hardware and that sort of thing. N1MM is a perfect example of one where the developers have really taken Ethernet and the capabilities of the internet to heart and put all those capabilities inside the logger. So excellent.
Excellent. And they've even got distributed operations now, where HP3SS did a great station out of Costa Rica, and most of his operators were in the U.S. and Canada other than him. And they were all logging away, like they're sitting at home and operating, and it worked out really well. So our hats off to those guys. And they're not the only station. It's just the one that came to the top of my head, because I know Robbie personally, who's from Canada, that moved to warmer climates. I guess he got tired of the snow. I guess we all do. We're almost done here. You've spent a lot of time with your head in the government world, and they're obviously reaping the benefits that amateur radio has bought, right? Because they're much more distributed than we are. And I guess in an earlier world, if you were working in the government world and you were sitting there monitoring RF spectrum, you had to be sitting at the radio. Now that's not the case, correct?
That's right. Yeah. The government project's really neat, the one that we've been working on the last couple years. And it's really cool because it's not very often in your career that somebody hands you a sheet of paper and says, build the coolest thing you could build. We're interested in buying it. And so this is kind of what we've done for our government customer. And I hope they're very pleased with what we've designed for them. But it also gives us the capability, some of the things that we've designed, we can roll back into amateur products. So we're very much looking forward to being able to do that in the future as the next couple of years tick through.
Yeah. And how many meetings have you been into that there's been an amateur there that knows Flex Radio already? Has that been sort of the catalyst that's pried the door open?
Yeah. When I was, we went to the ARL Centennial, I think it was, conference that they had in Connecticut here. It's been probably 4 or 5 years, and they had the head of FEMA, Craig Fugate, talked, and he got up at dinner, and there were probably, 300 people in the audience, and he said, "How many of you has your career been influenced by becoming an amateur radio operator?" And like 2/3 of the hands went up, and it's definitely the same thing when we work with the government and anything RF related. There's a sizable portion of those people that are hams, and the great thing that ham radio gives you is a really practical view of RF. You spend a lot of time messing around with RF and antennas and power sources, and trying to make everything work, coaxial cables, all that kind of stuff. You learn a lot, and that is it's like on the job training. And whenever you look at getting a job that has any RF in it, you could say, "Hey, I'm a ham. I know all this stuff." And that's a really great thing. It is one of the key goals that in the charter for Part 97 in the U.S.
Wrapping up, we haven't mentioned this in a long time, but we actually have a radio in space.
We do. We have 2 radios in space, actually.
Mm-hmm.
There's on board the International Space Station. There are 2 Flex 6700s that originally went up as part of an experiment to be able to watch ships at sea. There's a communications protocol called AIS, which allows ships to broadcast their position, and shore-based receivers to receive that and then plot where they are on a map so you can track ships. But because it runs on VHF, you get very far from shore and the propagation isn't there, and the ships can no longer be seen. So what we did was we put a couple of Flex 6700s on the International Space Station, And we actually use all 8 receivers on both of those radios. And what happens is there's 2 key AIS frequencies. And so we take all those multiple receivers and place them before and after in frequency each of those channels for Doppler shifts. So if the space station is traveling towards a ship, the frequency is going to increase some. So we have a channel allocated that would pick that up. And then if the space station is moving away, the Doppler shift would be negative, and the ships would show up on a lower frequency. So we use all 8 of those receivers. The data gets collected on the International Space Station and then sent to ground over the TDRS network, where then you can see all the ships that are traveling anywhere in the oceans around the world.
I thought that was pretty cool when you told me that before, and then you thought, how many ships do you track at one time? Or can you say? It's a lot.
Yeah, it's a lot. The map is really interesting to watch, and you can see there's little dots on the map. You can see shipping lanes where the ships are traveling between 2 common ports, and it's really interesting to look at it.
Yeah, I can imagine. And so who gets to go on the next service call?
I don't know. I'm certainly, I have my name on the list. I'm not sure they're going to let me do it, but
yeah, I bet you most of us would be, I don't care, I'm going. It's like,
maybe it needs a software upgrade to support all the ships that are backed up. When we get ships stuck in a canal or something. I don't know.
Yeah, that's very cool stuff, and there's a lot more going on. Steve, I wanted to thank you for your time. We see so much in this industry, from amateur feeding, commercial, and commercial even more so will feed back to amateur. And I think you guys are in a great position to be part of that. And I know literally the phone rings off the hook because I get some of those phone calls because I'm sort of the default extension. So it's a good position to be in.
Yeah, it's really a lot of fun. We're having such a great time, and you mentioned amateur and commercial or government opportunities feeding into each other, and it's really true. It's neat because we can try out brand new technologies in the amateur world that are not yet mature, that the government might not want to go use in a production kind of product, and try them out in the amateur world. But we can also do new things for the government that are things they've thought of that we haven't done in the amateur world, and learn how to do those things, and when it's possible, bring those back into the amateur world. So it's really a great synergy, I guess is the word I would use, between the markets. Very good. Well, I wanted to thank you for your time. I know you had a busy day, and the phone only rang once while we were here. I think I'll take that out, but have a great day, everybody. Thanks for joining us at the QSO Today Expo. And this is Steve Hicks, N5AC, who's been my guest. Today, I'm Mike, VA3MW. Steve, thank you. Hey, thanks, Mike, and appreciate all you do. Have a good one. All right, 73, everybody.